quick mic check. Okay, I think we're okay. Good morning. Can only see one person in the chat, so good morning to you, Glazer. Good morning to everybody else who's watching. I hear the maybe power outages, so I hope that's not affecting you. Good morning, Tyler. If you are affected by the power outages, of course, if it's affecting your ability to complete coursework, then let your instructors know and see what they can do to work with you. Morning, Gersovax. So anyway, it looks like a few of you at least still have your electricity, so that's good news. Anyway, I hope that you are all well. Hope you're having a good start to your week. Although for some of you, I know that there may be the threat of a power outage, so fingers crossed that doesn't affect any of you guys. I was going to do a little week-by-week countdown thing, but like where I track it on the side, so I may add that for next week. Just because it sometimes is good to remind yourself that you're making progress, you're getting there. So we're getting there. We're doing quite well as a group, so thanks for your continued efforts. That everybody in your class turns in everything every week is pretty remarkable, so thank you for doing that. It's certainly encouraging for me to know that you're out there and you're still doing the work, and hopefully occasionally at least, if not on a regular basis, learning something new. In this class, it may not be obvious always where you can use this information, but I have become a better programmer by learning this stuff and teaching it, and hopefully you will find that you make better use of these technologies, knowing a little bit about what goes on under the hood, and also adding a few things to your toolkit, like bitwise operations. Okay, anyway, so let's do the regular walkthrough or what's going on this week. So we are in week 10. The concept of 2's complement is it is one of the ways that negative or signed numbers are represented on computers. So this week we add signed integers, which means that we now have negative and positive, whereas before, of course, we were using unsigned integers, which were always 0 or above. So now we're adding negative numbers, and you'll see how those are represented on the computer, and some of the implications of that. So they still have limits. Signed numbers still have ranges of values they can represent, just like unsigned numbers. They're just different ranges because the range now extends to below 0, something negative, up to some positive number. So that's what we mean by 2's complement. It is a system for representing signed integers on a computer. Week 10. So let's do the walkthrough, and then we'll I got to draw pictures this week. Hopefully you're adapting to my old school style of drawing pictures. Again, I've tried the drawing pads, and I'm just not any good at it, and I end up spending more time fighting the pad than just using a pencil and paper. So that's what I choose to do in the interest of efficiency. Okay, so our goals for the week. Okay, thanks, Tyler. I appreciate it. Hopefully I'm getting in better habits about drawing the symbols and stuff bigger, at least. Okay, so the goals for this week look like a lot, but mostly it's just because we sort of always have a concept, and then we always have some application of the concept in HLA code. In this case, I'm just we're continuing to explore a little bit bitwise operations, so those are back in the list. So there's a question in chat, am I going to teach class in winter? So no, I'm not. And in fact, I'm not teaching class in the spring, so when this semester's over, I won't be back until the fall of 21. So I'm sort of slowly heading toward my retirement, and this is part of it, is sort of winding down my annual teaching work. So after this semester's over, the next time I'll be teaching classes again is in August of 2021, actually. Okay, so we're doing 2's complement. We're also going to add in binary addition. Just knowing how binary numbers are added, what are the rules for doing addition, I actually find it helpful to do binary addition in at the same time that I'm working in 2's complement. Because it turns out if you add -1 to 1, you get 0. So knowing how that works is just kind of good confirmation that your 2's complement understanding is going okay. Anyway, we'll keep doing bitwise operations just so you get some more hands-on practice with that. And then we'll finally have an HLA program that can handle negative numbers this week. So that's sort of the overarching goals of the week. So it looks like there's more reading than normal, but it's in part because I just thought that the book needed a little bit of help on the details of doing binary addition and what we mean when we're talking about how to represent signed or negative integers on a computer. Now, homework is always drawn from the 3 readings. The lab, which I'll come back to, and get you started on that. What are we doing in Piazza? Oh, so this is one of those where just sort of pick a thing and add to the conversation about it. So at least it occurs to me sometimes, like, where did 2's complement come from? Did someone invent it? Did it just sort of appear out of nowhere? And of course, all these systems that we talk about, the decimal system, the hexadecimal system, the binary system, 2's complement for representing signed numbers, those all came from somewhere. The new one, the new kid on the block, as it were, is the qubit. So if you don't know what a qubit is, you might go look into that. That's something that may or may not appear in your working life, but it may appear in your working life. So it'd be nice to know what that is, should it appear. Also, by the way, the concept of 0 was invented, had to be invented. Anyway, so that's what that's about. So just find something, hopefully something that someone else hasn't already added to the discussion, and talk a little bit about where did that system come from. I didn't put octal in here, but you could add that one if you wanted. So that's the discussion. It's one of those sort of brief research things. And then the reminder, so the second individual project is a ways out yet for us, but you should go read the specification for it sooner than later, and then start looking for the building blocks for it each week in lab. And I'll point out this week's lab has a couple of things that are very similar to last week's lab that can be used on the second project. Okay, so I'm going to switch my setup here and do some of the pen and paper stuff. Document camera, Firefox. Okay, so I'm actually going to start with binary addition. The rules are fairly simple, but I also want you to keep straight the difference between, hopefully that fits okay, the difference between bitwise operations and binary addition. So it's unlikely you're ever going to actually need binary addition. Just use decimal numbers to do math. But when you're in an assembly class, it's important to know the difference and to understand what distinguishes bitwise operations from binary addition. We're not going to do binary subtraction, and we're not going to do binary multiplication or binary division, just binary addition. Even though you could do those operations, that's the only one we're going to worry about. The main thing that makes these different is that bitwise operations have no concept of carry. So if I do, for example, the binary value 1001, 0111, and the bitwise operation and, the operation just works on pairs of bits, and there's no concept of part of the result of one column carrying over into another. So bitwise operations, no carry. in terms of the operation, right? So 1 and 1 is 1. That's it. There's no part of that result that carries to the next column. 1 and 1 is 1. That's it. 0 and 1 is 1. Nope, sorry, 0. And that's it. There's no carry. 1 and 0 is 0. So just remember that when you're talking about bitwise operations, it literally just applies to the pairs of bits. Now binary addition does have the concept of carry. So you do have to account for part of the results of one column carrying into the results of another column. You know how to do this with decimal addition. Same concept, you just have to remember that in a binary number, a column can only represent up to, it can only have 0 or 1 in it, whereas in a decimal addition, it can have 0 through 9. Anyway, so if you add 1 and 1 together, you get 2. But in binary 2 looks like this, right? So if you add 1 and 1 together, you get a 0 in your current column, and then you have to carry a 1 to the second column. So remember that. Binary addition does have the concept of carry, just like other addition, decimal addition does. So 1 and 1 and 1 is technically 3, which looks like this in binary, right? So 1 and 1 and 1, you write down a 1 and then you carry a 1. 1 and 0 and 1 is 2. So you write down a 0 and carry a 1. And then 1 and 1 and 0 is 2, so you write down a 0 and carry a 1. And on the processor, you know this now because we've used it to detect when the result doesn't fit. On the processor, it keeps track of when carries happen, of course. So in this case, there's a carry bit, which means that the actual result did not fit in the number of bits you were using. So the actual result doesn't fit in 4 bits. The actual result is that extra bit and then this part. But that didn't fit in the 4 bits we were working with, so that's just considered a carry, which in code we would detect and say, oh, there was some error happened because we didn't have enough space to store the result. So that's binary addition. I'll do the simple rules. Which are pretty simple, but let's do them anyway just to be on the safe side. So 0 plus 0 is 0, not surprisingly. 1 plus 0 is 1, not surprisingly. This is like literally straightforward math. I just want to make it clear as possible. 0 plus 1 is 1, as you'd expect. And then finally the special one is 1 plus 1 is actually 2, but what we end up writing down is 1 plus 1 is 0 and it carries. So if I'm only using 1 bit to represent the result, then my result of adding 1 and 1 would be 0 and a carry. So that's binary addition. Now that's useful because we're going to use it to confirm that our understanding of what comes next is correct. But don't get it confused with bitwise operations that do not carry. Bitwise operations do not have carry. They just apply the column, the column, the column, the column. There's no concept of something carrying over to the next column with bitwise. With binary addition, there is. Okay, so that's binary addition. And again, don't get it confused with bitwise operations because they don't work the same at all. Okay, so now we can add the actual sort of big new thing, and that is 2's complement. All that is talking about is how do you, if I want to store a negative number on a computer, how do I do that? So the way you do it is this. It's the same bits. The only thing that changes is how you interpret the meaning of the bits. So the reason I wrote those down like that is in part just to point out to you that 2's complement is just a binary numbering system. The only thing that changes with 2's complement is how you interpret these bits. So in 2's complement, this highest most bit is the sign bit. So in the 2's complement system, instead of counting this bit as part of the value, you only count it as an indicator of positive or negative. So the lower bits are the value. So these are the value, this is the sign. When the sign bit is 1, or yeah, I do want to write that, negative. So when the sign bit is 1, that's a negative number. You know that automatically. When the sign bit is 0, it's a positive number. So just for starters, that's the most basic thing about 2's complement, is that this uppermost bit is reserved to represent positive or negative. Negative when it's 1, positive when it's 0. That's the most basic part about it. Now, what makes this tricky is that it changes the meaning of the value bits a little bit. Yeah, it just does. Kind of changes the meaning of the value bits. And I'll show you how to derive that. So let's start with the easy ones, which are the positive numbers, and then we'll do the negative numbers. But the thing to remember is this uppermost bit represents whether or not the value is positive or negative. 1 is negative, 0 is positive. Okay, so let's, still doing 2's complement. And I'll show you in code here in a second, but if the number is 2's complement, then you kind of have to be aware of that fact as the programmer. You have to tell the computer you mean for it to be assigned value if that's important, and I'll show you where that happens. All right, so let's do some positive numbers. I'm just making these up. So how do I know these are positives? Because these are 0. So these are all positive numbers. Simply because that's a 0. They're all positive. Okay, so the rest of it is the system you are familiar with. I could do it in hex if I wanted to, by the way. So I could take these bits as hex, which is, that's 1 and 4 is 5. And then these bits are 8 and 1 is 9, so that's what it looks like in hex. In decimal, that's 1 plus 8 is 9, plus 16 is 25, plus 64, 64 and 25 is 89, I think. 64, 25, 89, probably. If I mess up the math, please someone correct me. The point here is it's the exact same as you're used to. When it's a positive number in 2's complement, it is the exact same as you're used to. Let's do this one real quick. So if we do it in hex, that would be 0. This one would be 15 or F. That's it, positive. Or positive in decimal, 15. So no difference. The positive ones are no different from what you're used to. This last one in hex, that's 5 and that's 5. Or in decimal is 5 and 16 is 21 and 64 is 85. So no difference when it's positive. When it's positive, it's super easy to interpret in the raw binary because it's the same as you've learned right from the start of the semester. One thing we will do is point out the smallest positive number you can do. Not surprisingly is 0. The biggest positive number you can do, positive, and then all ones. Now I just happen to know that this is 127. So that's the biggest number you can get with 2's complement 8 bits. Or in other words, the biggest signed 8-bit integer you can have is positive 127. Just by writing that down. So those are easy. Now let's do scary hard ones. Did I write 2's complement on that? No. Okay, so now let's do scary harder ones. Negative ones. They're gonna be negative. We know that because they're all gonna have the sign bit be 1. And let's just do something that looks relatively easy like this. Okay, so this is negative something. Now in hex, it looks like this. But in decimal, it looks like something completely different. So the hex representation doesn't change. That's an 8 and that's a 0. But the decimal representation is quite a bit different. So there's a process, there's an algorithm to figure out what this means. You could, if you wanted to, memorize what this is in 2's complement. It's not what you think it is. But the easier thing to do is to learn the process. So how do I take, if I'm told that this is 2's complement, I know it's negative, but what do these parts mean? So here's the algorithm to figure that out. The way you figure this out is that you apply the not operation to it, which gives me this. So you apply the not, and then you add 1. Add 1. So that's why we started with binary arithmetic. So now we add 1. So why are we doing this? Because we don't know what this means. So remember that. If I'm told that this is a 2's complement value, the only thing that's easily figured out is whether or not it's negative or positive. It's negative. But in 2's complement, the rest of the bits for value don't mean what you think they mean. You have to actually apply an algorithm to figure out what they mean, at least in terms of getting the decimal out of them. So if I want to know what a 2's complement value is in decimal, I first start by knotting the value, which is to reverse all the bits. So the ones become zeros and the zeros become ones. And then as a second step, I add 1 to that. If I add 1 to this, I end up with this, which is 128. So the only way to know from the binary what this value means as a decimal number is to apply this process to it and figure it out. I know it's negative, but negative what? This not add 1 tells me negative what? It's negative 128. Turns out, by the way, that's the smallest value that you can represent in 2's complement. All right, so now let's do another just to see what it feels like. So I know this one's negative. If it's 2's complement, which I'm telling you it is, then I know this is negative because the sign bit is 1. So in hex, it would look like this. Doesn't really help you because really hex is just shortcut for binary. So what if I wanted to know what that kind of means in decimal? And actually I'll ask you as a means of slowing myself down. And good morning, if I didn't say good morning to you and you showed up since the good morning. Good morning, everybody. So let's do a little bit of review together here. So how do I figure out, I know the sign, that part's easy, but the value in a 2's complement number is not what you think it is. So how do I get what this looks like in decimal? I know it's negative because of that, but how do I get what this looks like in decimal? Not the bits. So good one. It's perfect. Not the bits gives me this. Then add 1. Good one, Glazer. And then I will add 1. So I end up with this, which means what's my value? Negative. So what do I write there? Negative 1. Good one. Okay, so it seems really crazy, but I'm just telling you, 2's complement, when the number is negative, the bits don't mean what you think they mean. So you have to go through a process to figure out what they mean. So you take the 2's complement value, you know it's negative, so you can write that part down. Then you take and apply this process. You knot the bits, add 1, and the result is what your value means. That's exactly right. So Glazer's asking, is this the largest negative number I can do? And the answer is yes. So this value right here is the largest negative you can get in 2's complement, in 8 bits 2's complement, right? Which makes sense because from there you get to 0 again. So it's really weird. I'm just reminding you that when we're talking about 2's complement, when we are talking about the binary for signed integers, the negative numbers are weird. The bits don't mean what you think they mean until you've applied a process to them to figure out what they mean, unless you memorize this stuff. Which I would never do, but if you memorized it, then you could just say, oh, that's negative 1, I memorized it. Or you apply this process and you're like, oh, it's negative, apply the process, negative 1. You can go the other way, by the way. So we know that this is, well, let's just start with this. No, let's do the What do I want? Another way of saying what we've just done, if we don't really care what the meaning is, we just want to say, hey, let's reverse the sign. To reverse the sign of this 2's complement number, we not and add 1. So that's really what we were doing, is we were taking a negative number and reversing the sign. So it's kind of like multiplying a number by -1, right? So if you were to multiply this by -1, you'd get this. That's all we actually did, is just reverse the sign. You can go in the other direction. So we could ask a question like this. So for example, what is -99 and 2's complement? How would you ever in a million years get that? Well, I know one part for free. I know that it's negative, but the rest of it I'm going to have to figure out. So how do we get 99, -99 in 2's complement? So the easiest way to figure out what is -99 in 2's complement is to start with the positive version of it. So what's positive 99? That's relatively easy to do. So always start with the positive one. Positive 99 looks like 64. So 64 and a 32. No 16. 64 and 32 is 96, so I owe it 3 more. All right, so there's positive 99. How do I get to the binary 2's complement of -99 from here? So start with the positive, because that's easy to do. Not, good one. Not it. Okay, that's perfect. So there's the not, and then add 1. Perfect. Good one, Glazer. Add 1. So if I add 1, that becomes... So there's -99. So if you're doing pencil and paper work, you want to sort of get the positive ones, because those are easy to derive and understand. And remember, in 2's complement, if there's a 1 in the sign bit, then these bits don't mean what you think they mean. So it's a lot easier to get back to the positive version of it. I usually start with that. Oh, you want -99? Well, I'll start with positive 99. That's easy. And then I will not it, and then add 1, and then I can tell you what it is, -99. All right, so one last piece of, I think we're doing okay on time. Yeah, so let me show you go back to binary addition and show you the magic here. So we get these two values, so 99, 0, 1, 1, 0, 0, 0, 0, 1, 1, that's positive 99. Negative 99 is 1, 0, 0, 1. 1, 1, 0, 1. Okay, so here's positive 99. So here's a way to confirm that you got it right, is you add the positive and the negative ones together. And if you do that, what ought to happen? Like, what happens if I add positive 99 to negative 99? I should get 0. Good one, Glazer. So this is why we started with binary addition. If you want to know absolutely for certain that it worked, then do binary addition and you should get 0. So 1 and 1 is a 0 with the carry. It's a 0 with the carry, it's a 0 with the carry, a 0 with the carry. So it seems a little unsettling that you get a carry here, but that's okay actually. You get 0. That's correct. There is a bit that got carried out, but in 2's complement that's okay. So you do get a carry, but the result is 0, and that's what you wanted. This doesn't mean anything in this case. Okay, so there's why we started with binary addition also, as we can confirm. So let's do one more, and then we'll go to code. And of course, a lot of this stuff is kind of artificial, just for teaching purposes. Remember that you're not likely to be asked these questions in an interview. But let's say we wanted to do 99 minus 42 in binary. So if someone asks us to do 99 minus 42 in binary, let's reimagine this problem with the tools that we now have available to us. Sorry, my voice is messing up a little. Oh, let me clear my throat. Oh, you could hear that. Sorry, I meant to mute the mic, but I didn't. Anyway, okay, all better. So there you go. So if someone asks us to show this in binary, the first step is to reimagine it as an addition problem. And as soon as we do that, we realize I need 2's complement. Now 99 we already know. That is a 64 and a 32, and then 3 more. The 42 is a bigger pain in our rear to get. We know it's going to be negative. So to get the 42, well, start with the positive. Let's see, no 128, no 64. It does have a 32, which leaves 10 more. So an 8 and a 2. That's positive 42. Not. Add 1. So there's negative 42. So 1, 1, 0, 1, 0, 1, 1, 0. And then we end up with 1 and 0 is a 1, no carry. 1 and 1 is a 0 carry, 0 carry. 1, 1, 0 and a carry, 0 and a carry. But let's see if that matters in this case. So our result is 32 plus 16 is 48, and 8 is 56. 57 is our result, which is correct. Now all of this handwork that I'm doing with the pencil and paper is just for teaching and learning and understanding purposes, you're not likely to ever sort of manually do binary addition. This is just to kind of show you how, what the computer is doing with this stuff. So there's the non-code portion of the course. Binary addition and two's complement, which is a binary system for representing signed integers. Now they can be positive or negative, but of particular interest are the negative ones. Okay, so that's that part. So now let's switch over and look at a little bit of code and just get the brain working a little bit around that problem. So give me a second to switch up my view. Okay, I think we're all set up. So I'm going to do just some bare coding with some examples, and then later I'll pull in the lab and get us started on that. Well, let's look at it in code before I start just yakking away about that. But I also got to see that you can see what I see. Okay, I think you're okay. Knew that I was going to do that. Sorry, I'm doing some window fixing here because I haven't logged in yet. Okay, here we are. So let's sort of look at this from the code perspective then. What does it look like to have negative numbers in a program? And also just to show you some tricks and get you thinking. I don't know if that works that way for you guys. I don't know if you can see the text editor takes a little bit to start up, which is interesting. So program, I'm already regretting that name because it's hard to type. Make sure you can see. Okay. Sometimes I forget, so if you can't see, please let me know. And then I'll call it twos.hla. Make sure it gets in the right folder. Okay, so as a starting place, the thing to remember about two's complement is that ultimately it's binary. And the computer, in most cases, doesn't care less if it's positive or negative. The computer doesn't really care. And I think you saw, at least in the case of doing addition, that the results look the same. If I add two binary numbers together, whether or not they're two's complement, the math works the same. So the computer doesn't actually have to do anything different for basic addition or even subtraction, as it turns out, on binary numbers. If it's two's complement or not two's complement, the computer doesn't care. So when does it matter that it's two's complement? It's mostly, it matters when you're doing multiplication, it matters when you're doing division, and it matters when you're doing outputs. So I'm going to do some examples of those things. Well, I'm not going to do the multiplication and division. Those come up, I think, soon. But let's leave that alone for now until we get to it. Well, we'll see. We'll see what I have time to do. Okay, so anyway, be thinking to yourself that much of the time the computer couldn't care less what the binary number means, how it's supposed to be interpreted. And let's just do a quick example of that. So you can type in HLA, you can type binary values. So I'm just going to type 1001, 0110, and I'll move that into AL. So at this point, that means nothing to the computer. It means nothing. It's just data. It's just bits, some of which are turned on and some of which are turned oh, did I mute? Mic check. My mic's on. Can you guys hear me? Okay, check on your end and see if you're having a. So yeah, the mic's on. I think we're okay. All right. So if you miss some of the audio because something is going on your end, the video will be just sort of mark the timestamp. So we're about 45 minutes in. So 45 minutes past the countdown timer. So just make note of that you lost audio somewhere around 40 to 45 minutes so that you can fast forward to that in the video. Sorry that's happening, that you lost audio for the time being. Hopefully you get it back soon. And we're not going super fast, so maybe if you disconnect and reconnect, you'll get it back. Okay, so remember that in most cases the computer doesn't care what the value means or how it's to be interpreted, it's just bits. So one place where you can, as a programmer, cause the interpretation that you want is in your output. So you can, for example, cause the value to be interpreted as unsigned by doing a typecast on it. And this is really the programming language at this point doing this, but you're telling the programming language, take those bits and interpret them as an unsigned integer. But you can also, as the programmer, use your programming language to force it to be interpreted as a signed integer. So it's the same bits, but in the first case, you're telling the program to interpret all of the bits as part of a positive number. In the second case, you're telling the program to interpret the bits as a possibly negative number. So when you use this int8 data type, you are using 2's complement. When you're using the uns8 data type, you are using all or positive. Okay, good. So we got our audio back. Hopefully you only missed a few minutes there. But there wasn't a whole lot of content. The main thing we've been talking about, Gersevak, is that when you load up some binary into a register, the computer doesn't really know what it's supposed to mean or care in most cases. And the way to get those bits to mean something to be interpreted is in your own code. So one of the more obvious ways that you can cause the bits to be interpreted in different ways is with output statements and typecasting. So if I type to uns8, then all of the bits are considered to be part of a positive number. And in uns8, that upper bit just means value. With int8, however, what you're telling the program to do is take that upper bit and interpret it as meaning positive or negative and apply the whole 2's complement process to it. So these are going to look different. So as an unsigned integer, that's 150. As a signed integer, that's negative 106. Now we could do the handwork for that, but I don't know that we necessarily need to at this point. But anyway, how does the computer know that it's 2's complement? It doesn't. It only knows when you tell it to do it. So we can do things like add. Let's do that in binary. So we can add these bits to it, and then all it's going to do is apply the binary process the binary addition process, and then if we repeat the outputs, they should make sense, but they may not make sense, so let's just see. So in this case, they made sense. The unsigned went up by 10, the signed went up by 10. That's all okay. If we were to add this value, I'm not going to do it, but hopefully you can imagine that this is going to wreak havoc possibly on both values. So it came back 32 in both cases. We could do the math, but anyway, the point is, one of the ways that you can force the computer to interpret the bits the way you want them to is in your output statements with the typecast. And if you do addition, it makes no difference if it's 2's complement or not 2's complement, because binary addition works the same on any binary value no matter what system of representation you're using. So if we're using 2's complement, it doesn't change the result. If it's all unsigned, it doesn't change the result. Same works for subtraction. Now where it does make a difference is when you're doing multiplication and division, and I didn't leave a whole lot of time to deal with this problem, so I'm going to have to come back to this so I can give you some tips on the lab. But I will tell you, and I need to make sure that I come back to it, doing multiplication and division is different. In fact, let me just set up one so you can see how scary this looks. Let's do this on a variable instead. So I'm going to use int 8s instead of uns 8 so I can get negative values in the mix. Let's say 2. So I have x, which I have initialized to negative 10, and y that I've initialized to 2. Okay, so adding these things, doesn't make a difference, although I will tell you that when you move x to AL, it just moves the binary. So if you were to still turn around and interpret it as a signed integer, it would look like whatever those bits look like. So let's not do that. But anyway, now let's do a little bit of math. So addition doesn't change and subtraction doesn't change, but what does change is multiplication. So let's do a multiply. So I'm going to say I'll move, it doesn't really matter, but I'll move x into AL. And then I'm going to eyemall y with AL. So this is another way that you tell the computer what the bits mean. With some instructions, eyemall is an example, you tell the computer that this is signed or 2's complement values. So if you want the math to work correctly on the processor with multiplication, you have to tell it that these are 2's complement. And you do that with a different instruction, in this case, eyemall, and then we'll print it out. Okay, so what I'm telling you here is that how does the computer know if it's 2's complement or not? It doesn't. You have to tell it. So when you're doing outputs, you can tell the computer what you mean by using a typecast to the appropriate data type. If you're doing multiplication, then you tell the computer to interpret them properly using eyemall for signed. The addition is no different, and the subtraction is no different, but multiplication is. So 2's complement multiplication has its own instruction. Oh, I got it in hex, dummy. I got it in hex. There's what it was in hex EC. But let's do that better. Okay, so negative 20, that's what we expected. So how does it know it's 2's complement? It does not. But it usually doesn't matter with a couple of exceptions. Doing outputs, it matters. Doing multiplication, it matters. And then the real scary one is doing division. All right, so now let's do division. Nope. So division is another one where if you mean for it to be 2's complement, it changes things. And you have to use a different instruction. So using this instruction, I'm just going to show you one example today, and then we'll come back to more to lengthier examples in the future. Just wanted to point out to you that you tell the computer that you're using 2's complement with instructions in the cases where you have to do that. IMUL is one, that's the 2's complement multiplication. IDiv is another, that's 2's complement division. So you still load up the numerator, but then the next step is different. So we do and I'll show you quickly on paper what I just did after I do this example. So the zero out AH changes for 2's complement, and we have to do instead what's called sign extending. And they have their own instructions. Now this is the first time you've seen this, so don't worry about it. I just want to show you that when you're doing 2's complement, there are some cases where you have to be careful to actually tell the computer you're doing 2's complement. Outputs is one, multiplication is one, division is one. What the CBW actually stands for, by the way, is convert byte to word, but don't worry about that right now. We'll do an extended example in the near future. Anyway, load up the numerator. Now for 2's complement, instead of zeroing out AH, I sign extend it. Then I do the IDiv. And then I can do the output. So x divided by y equals typecasting, to be careful, and then I can say remainder so AL still has the quotient, even though it's IDiv, it's still the same, but I have to typecast it to make it look like 2's complement. And then the remainder still goes into AH, but I have to typecast it because I'm using 2's complement. Let's see, close. Okay, so there's that. Now we know that the answer should be, well, let's just see if it gets it right. So negative 5. So 2 times negative 5 equals negative 10, so that worked. So don't worry about these examples just a whole lot. We will look at how to apply these in the second project. The point here is, how does the computer know that I'm using 2's complement? It doesn't. You have to tell it in the cases where that is required. Outputs, you have to tell it. I'm using 2's complement. Multiplication, you have to tell it. I'm using 2's complement. Division, you have to tell it. I'm using 2's complement. So that's how the computer knows, is that you told it. In these cases, in all the other cases that we will ever encounter, it doesn't matter. So bitwise logic doesn't change with 2's complement type values. It doesn't care if it's positive or negative. Addition doesn't change. Subtraction doesn't change. We will see at some point that if statements and loops change, but we'll worry about that then. For now, just how does it know? I have to tell it. Okay, so that's a lot of stuff. Hopefully I didn't overwhelm you too much with that. We're going to come back and talk about IMUL and IDIV in the context of the second project, so you don't really have to worry about those much right now. IDIV is the scary one, but it's not that scary once you've seen how it works. Okay, now let's do the, how am I doing on time? I'm going to run over a few minutes, but let me just make sure that we have a fair start on the lab for the week. So let me go grab that code and have a quick look, and if I think that you might need a starter, I'll do that. What I'm doing right now, I didn't bring it up, but I'm going to grab the code. So I just clicked the link in Canvas, and I'm now copying the code over. Okay, so lab 10. I'm just going to go through this and review it with you. So the variables this week are signed. So these are 2's complement values, which means that they can do from negative 128 all the way up to positive 127. The second project uses signed integers, I think, by default. So anyway, now we can do positives and negatives. I did an update, by the way, the documentation here. It should say intate. Reads in an intate, which matters, and the key piece here is this right here. So we're doing get I8, which is get signed 8-bit integer. I8, not U8. I'll update this intate on the repository. So get I8 is the big change, but this function is completed already, so that's just a matter of noting where it's different. Printing in binary and decimal format, that's already been done. The parameters changed to int8, but the code doesn't. Like this loop for printing out binary, it doesn't care if it's 2's complement. It's binary, it doesn't care. So it's the exact same procedure or the exact same algorithm. And then down here, where I'm putting out the value, because that has the int8 data type attached to it already, HLA knows to put that out and interpret it as 2's complement. Now, if I were putting out a register, I would have to typecast it. But since value is already has the int8 type attached to it, HLA will do that properly. That one's already done as well. These first two, again, sort of building blocks for the second project. You're going to want some procedures to get numbers like this. And you're going to want the ability to print out values in their binary format. Go again is as it was last week. Nothing new there. That's already been done for you. All right, so let's look at where the tricks are. Okay, so add number 1 and number 2. Use AL as a middleman result. So the main thing to remember here is that adding signed integers, adding 2's complement, doesn't change anything. It's the same thing. It doesn't change anything. So that's the point of this little exercise, but also if you put in a positive 1 and a negative 1, the result should be 0. So you can experiment with that. But adding 2's complement doesn't change anything about how you write the code. Now notice when I do print binary and decimal, I pass in AL. You can typecast it here, but what happens is that if the procedure receives a register as a parameter and it's typed, it's going to sort of typecast for you. So as soon as that AL arrives at the procedure, it's going to be typecast into int8. So that takes care of itself. So that part with the move and the add are done. 2. I'm probably going to steal all the fun from you, so sorry about that. Although I guess you could stop the video here if you don't want a spoiler. So the process of reversing the sign. Well, let's use AL as a middleman. so that we don't mess up our value. That's just to leave number 1 intact, so we're going to put the bits in AL. Then we just knot the bits and add 1. Sign reversed. And the same thing here, it's going to print the result as an int 8. So that's the solution to part 2, is you put the bits in AL, then you knot those bits and add 1, and you've reversed the sign. If it's 2's complement, which this procedure will treat it as. Negate. So there is a function that does this all in one step. I just wanted you to see the knot and add 1 process so you understand how it works. But you can also do negate. And all negate does, if you might imagine, is knot and add 1. So Intel added this instruction just to make life a little easier if you find yourself doing this a lot. So that negates the value, but what it's really doing, of course, is it's not add 1. Yeah, I'm going to keep going. If you're okay to keep going, I'm going to keep showing you stuff because some of these are new applications of these things. So anyway, spoiler heavy in the video, so if you're watching later, here's another spot where I'm about to put a spoiler in. Okay, so now we're moving into just some applications of bitwise logic. Another thing to keep in mind, though, is that bitwise operations don't care if it's 2's complement or not. It really changes nothing about the way bitwise operations work. Okay, so what's it asking us to do here? It's saying use AND to clear the upper nibble, which is the upper 4 bits of number 1. Use BL to store the clearing value, and AL as a middleman. Okay, so that seems like a lot, but it's not too bad. So the whole process here is I want to AND number 1 with something. So the first thing I'm going to do is I'm going to load the bits of number 1 into AL. Let me do a quick... Sorry, I'm really asking for your patience today. Let me do a quick picture of what we're doing. So we're going to put some bits. We don't know what they are. It doesn't really matter. So the first step is we're going to put some bits in AL. The second step is we're going to put our clearing value into BL. So a clearing value means, and what it tells me I want is I want to zero out the upper nibble of this value. So what I actually want as a result is this. So I want to take the original value and I want to filter it through some value with AND that leaves me with this result. So that's what I mean by clearing the upper nibble. Take whatever it is now and turn it into all zeros. But I want to leave the lower nibble intact. So the question is, what value here would yield this result if I AND it with this value? So this value and what gives me this? And I'll let chat do it if there's anyone still around in chat. I think some of you are still here. Yeah, thank you for sticking around. So does anyone know what I should put here for my clearing value so that if I AND it with this, I get this? It's a tricky one. But when you see it, you're going to like, oh yeah, that's obvious. Close, Tyler. So yes, to clear a bit with AND, you use zeros. And you would get this result. So no matter what these start out as, if you pass them through zeros with AND, you're going to get zeros. Now this part is a little trickier. What we actually want is this. So if you use all ones, so Tyler was all the way up at the 1 bit. If you pass it through all ones, it preserves everything as it was. And the trick is, if I were to change this to 1, let's say that I change this to a 1, 0, 1, 0, then I would want 1, 0, 1, 0, and this still leaves everything intact. So when you're trying to clear bits with AND, you use zeros. If you're trying to leave them unaffected, you use ones. So this would be my clearing value. So you're 1 bit off, which is pretty good because this is new to everybody. So clearing is zeros. Preserving is actually all ones. So if they are zeros, they stay zeros, but if they are ones, they stay ones. So if I assume that I'm blind to this value, zeros are guaranteed to wipe them out. Ones are guaranteed to leave them where they were. So that's my clearing value. So now I can switch back here and show you how the clearing value is used. You can also, by the way, instead you could have done this. And use the hex for that instead. So that guarantees that I clear the upper nibble of number 1, and it guarantees that I preserve the lower nibble in whatever state it's in number 1. Then I simply apply the AND operation, so I pass AL through BL, and then AL will get the result, which should be the upper nibble is all zeros and the lower nibble is unaffected. The thing to do, of course, is to run this program, hopefully a bunch of times, and get a feel for it. So it's one of the reasons why I'm giving you the answers is I'm just as interested as that you run your program and think about what it's the output that you're seeing and how this is working. All right, so that's AND to clear bits. Here's OR to set bits. So OR is kind of exactly the opposite. So use OR to set specific bits. Use BL to store the setting value. Now in this case, it doesn't really care. It just wants you to examine the results. But I will tell you, let me switch the view again, and then I think we're almost done. Thanks for sticking around. Let's get the document camera back on. All right, so what happens if we do some arbitrary value ORed through something? So we're going to do a couple of examples here. So if I want to turn all of the bits on in the whole value, if I ORed like this, then it doesn't matter what they start out as, they are guaranteed to end up as all ones. But let's look at where we can sort of target more specifically. So 1, 0, 0, 1, 0, 1, 0, 1, ORed with something. Okay, so let's say for argument's sake that I want to turn these 2 bits on. And that I don't care about the rest. I don't care about any of these other bits. I just want to make sure that those flick on. So if I want to target specific bits with OR, then I literally target those specific bits. So if I do an ORing value like this, it leaves everything alone, but it guarantees that these come on. So if the original value was a 1, well, or with a 0 doesn't change anything. If it's a 0, then it turns on. 0 turns on. If you're ORing through a 0, it doesn't care. Doesn't care, doesn't care, doesn't care, doesn't care. So I've literally just targeted those two specific bits to come on. So this next problem is really just you pick an ORing value and see what it does. So we're going to use, so let's say use OR to say, okay, so move number 2 to AL. Now I've already zeroed out number 2, so that when you do ORing, you can see. So if I zero out number 2 and then I do an ORing value like this, this is the point. What would I expect AL to be at the end of all this? Now this is a scary one to venture an answer at because it's new to everybody. But does someone want to have a go at what AL is going to... So if number 2 is 0, so AL has all zeros in it, and I load BL with that ORing pattern, and then I OR AL and BL, what do I get as a result? Great one, Tyler. That's exactly right. So ORing, if you OR past a 0, nothing changes. If you OR past a 1 through a 1, then it's going to come on. So if I OR 0, which is what AL is, if I pass that through this pattern with OR, I'm going to get that same pattern back. So if I start with 0, OR with that, then I get that. Anyway, so that's kind of the point of this part of the experiment, is to just play around with that value a little bit and hopefully develop a sense of, okay, this is what's supposed to happen next, and see what happens. That's the whole lab, I think, is it? Did I leave anything? Ooh, XORing. Oh, I already did one. So I already left one, so I'm not going to do number 6 because you've already seen how it's done. So here I used XOR, just to show you this is one way you can use XOR, is to zero out all the bits in a thing. And then I left number 6 for you to try it for yourself. Okay, thank you very much for sticking around for the extra content. I hope you have time to take the lab code, since I just kind of ruined all your fun, and have fun in the running it and kind of getting a feel for what's going on with these bits. 2's complement. That's how you represent signed integers. And then we'll do more on that as we build up toward the second project, where we'll use signed integers, and I'll give you some help with how do I do signed multiplication and signed division, because those are different. Anyway, that's it for me. Thank you again. Thanks a lot for being here. Thanks for watching later, if you're watching later. I hope everyone has a great week. Let me know if you have any questions on a Canvas inbox. Otherwise, I will see you again next Monday. That is week 10. Next Monday is week 11. So we're getting way down to the short end of the semester. And pretty soon we're going to start looking for opportunities to get you kick-started on the second project. So that's probably next week where I'm going to try to squeeze something of the second project in. Okay. Take care, everybody. Thanks, and have a good week.